All right, so we're still going with some more exponential and logarithmic derivatives. So here's what we've developed in the last couple of videos. But we've got the exponential and the logarithm here, both base e, right? It's Euler's number, as it's sometimes called. But that's not the only way we construct exponentials and logarithms, right? We can have a logarithm of any positive base, and same thing with our exponential. So we now have some tools in place that we can figure out how to do those. So let's start with the logarithm of base b, right? So suppose I have y is equal to log base b of x, excuse me. Doesn't really matter, but x is more familiar. Remember what this means. This means that b to the y is equal to x, right? That's the definition, right? This inverse function, the logarithm. So here's what we're going to do with this equation. I'm going to take the natural log of both sides, right? We can do this. The exponential always spits out positive numbers, and so I can take the logarithm, the natural logarithm of both sides. Okay, and now we have to remember some of our properties of logarithms. So if you might recall that for a logarithm of any base, if we have something like this, the exponent can become come down in front and multiply the logarithm, right? So I won't prove this. You should have seen this in the past at some point, but it's related to the idea that, right, there's a relationship between exponents and multiplication, right? Remember, if I have something like x to the n to the m, this becomes x to the n m. Okay, this is a very related property right there. But for now, we just need to remember that this property exists. So what it means is I can take this y out front, not h, natural log of x. Okay. Now I'm going to take a derivative of both sides with respect to x. Okay, so let's think about what's happening on the left side. Natural log of b is just some positive number. The natural log of b is just some number. So that's a constant. So all we're doing is taking a constant times y and taking the derivative of that. So the constant can slip out front. And then we have left the derivative of y. The right-hand side, of course, we just use our rule that we developed. The derivative of the natural log is 1 over x. Well, what's the derivative of y? Here's one of those instances where we just write something simple or straightforward. The derivative of y is just, of course, the derivative of y. But this is what we're looking for. So we've got a constant times the derivative of y is equal to 1 over x. I can multiply both sides by 1 over the constant, and we get that the derivative is 1 over the natural log of b times 1 over x. Okay, so let's write this clearly. The derivative, what we've just shown, remember, we started with this. Y is equal to the log of some base b, and we ended with the derivative of y equal to this. So I can say this all in one line with the derivative of log base b of x is equal to 1 over the natural log of b times x. Okay, and there is our most general rule for logarithms, right? This is not a new rule, right? It agrees with this rule, right? Because in the case of the natural log, what is the base? The natural log is log base e. If we take the natural log of e, that constant just becomes a 1. And so that doesn't show up. We just have 1 over x. But for all other numbers, the natural log of everything else but e is something that's not 1, and so we get something else there. Okay. All right, let's try to do the same thing for our exponentials. All right, so now we're going to look at a more general exponential, where b, again, is some positive constant. We're going to use a similar trick that we used up here, which was to take the natural log of both sides. Again, we're using this trick because it lets us take something in the exponent, something that was an exponent, and turn it into a multiplication problem, and that's easier to deal with. So we'll take the natural log of y is equal to the natural log of b to the x. Now I will apply that property. Natural log of y is equal to x times the natural log of b. And now I'm going to take derivatives of both sides again with respect to x. Okay. All right. On the left-hand side, this is a chain rule. Y is a function of x. Okay. So when we put y inside the natural log, we're doing composition of functions. We're doing the composition of the natural log of x, and we're composing it with this y, this function y is equal to b to the x. So we have to use the chain rule. We take the derivative of the outside function, the natural log of x, the derivative is 1 over x. In this case, we're putting in y, so we get 1 over y. And then we multiply it by the derivative of the inside function. In this case, the derivative of the inside function is the derivative of y, which is just dy dx. We don't know what that is. It's what we're trying to find. Over here, natural log of b is a constant. So if you have the derivative of x times a constant, you just get the constant. Okay. So now dy dx. I'm just going to multiply y to the other side. We get y, let's write it in the other order, natural log of b times y. Okay, so now we have the derivative in terms of y, but we want it in terms of x, but we know how to do that. We know what y is. Y is equal to b to the x. We'll get dy dx is equal to natural log of b times b to the x. And so in summary, the derivative of an exponential of any base is the natural log of the base times the original function. And now we have a general derivative formula for exponentials, right? This also agrees with the rule that the derivative of e to the x is equal to e to the x, because the natural log of e is 1. And so that constant floating out front is just equal to 1. Think all the way back to a couple videos ago when we developed the derivative of e to the x. When we were first developing this, we ended up with the value of, we ended up with b to the x times the value of the derivative at 0, right? And we didn't know what this was. We defined the number e to be the number so that this is, of course, if b to the x is equal to f of x. We didn't know what we wanted. We defined e to be the number such as this derivative was 1, right? And we didn't know what this constant was for other numbers. And now we know what it is. It's the natural log of the base. That's the thing that that makes the exponential special, that constant, right? It's just a 1, and so it's its own derivative. The rest of them have this extra this extra constant out front. Okay. So now we have the ability to take derivatives of both of all logarithms and exponential functions with these two new rules. Something else nice happened while we were doing this. In both cases, we used this little method of taking the natural log of both sides. Right? We did it there and we did it here. And as I said, we did this because it helped us deal with a tricky situation. That is, we have something in the exponent that we want to get down, right? It's easier to deal with things. Exponents can be tricky to deal with. And so taking the natural log of both sides proved to be effective. This is a technique that we will use often. Let's do another example. Let's look at this function. Y is equal to x raised to the exponent sine of x. This is a very strange kind of function, right? So we have to assume the domain here is only positive values of x, right? We can only have a positive number. So I guess I'll just write that in. X is going to be greater than 0. So if we want the derivative of this, none of our rules work, right? It's kind of an exponential, except it's also got x in the exponent instead of a constant. It's kind of a power function, except instead of the power being a constant, the power is also a function. And so we don't know how our rules play with that. What we can do is take the natural log of both sides. And again, this is going to help us by by taking that exponent down and having it become a constant out front. And then we will take the derivative of both sides. The left-hand side, the same thing's going to happen that happened up here and that happened. Oh, I guess that's sorry, that's the only place it happened. Where we're looking at a chain rule because y is a function of x and we're putting it inside the natural log function. So we end up with 1 over y times dy dx or y prime. On the right-hand side here, we're going to have to use the chain or the product rule. So the derivative of sine is cosine, and we leave the natural log alone. And then we leave sine alone and take the derivative of the natural log, 1 over x. And now we just multiply y to the other side. So we get y prime is equal to y times the cosine of x, natural log of x, plus sine of x over x. And then finally, I can write this in terms of x because I know what y is. This is what we started with. Y is equal to x to the sine of x times the cosine of x, natural log of x, plus sine of x over x. Okay. So this is a pretty mysterious function in terms of taking derivatives at first glance, but this method of taking the logarithm of both sides is pretty handy. We call this logarithmic differentiation, right? For obvious reasons, we're using the logarithm. Let's take a look at this function and the derivative. So here is that function graphed. It's pretty strange, right? It's kind of, you can see that the sine is in here somewhere, right? Because it's got this kind of periodic nature, but it's not repeating exactly because it's obviously getting bigger. If I zoom out, we see that it just continues to get bigger. At this point, the computer just renders it as a solid. Let's see when it starts. You can start to see a little bit of the edge. There we go. Whoops. Okay, so there's our function. Oops, sorry. There's our function. Let's throw that derivative I just computed in here. And this blue line is the derivative. So let's zoom in close and take a look. Just let's see if it sort of behaves as we would expect it to. Let's look at this hump here. Right? You can imagine the tangent lines, which we'll graph in a second, but let's just imagine them first, seem to be positive, right? They're nearly 0 over here, and you can see the blue graph is very close to 0. It looks fairly flat over here, and then it increases, and the blue graph is getting higher for a while as these tangent lines get taller. But right before as we get up here, now we're getting less steep. By the time we get here, the tangent line we imagine would sit right on top of that peak, and we notice that the derivative goes through 0 there, right? The peak and the derivative, the peak is a place where the tangent line should have a slope of 0, and we see that exactly in the derivative there. Okay, and then as we come down the other side, we have negative tangent lines, or we imagine them. So let's put in a graph of some tangent lines. Right, so here's where it seems pretty shallow. That red line is the tangent line. It's pretty flat over here, and maybe this is moving too fast. Let me change. All right, there we go. So we can see the tangent line is pretty flat over here. As I move up, right, the blue dot is tracking the value of the slope. It's very high right now, but getting smaller. It hits 0 somewhere in there, and now it's negative. And here it's very, very flat, and that blue line is nearly 0. And now as it gets positive, the blue gets very positive until it's flat again, it hits 0, and then it keeps repeating this pattern. And this goes on and on. If we zoom out, we see that the blue graph kind of tracks that red one in the same way all the way through. There is also something interesting happening right as we approach 0. This is not defined there. 0 to 0 is not defined. But looking at the derivative, it appears that this, if we could zoom in with a strong enough program, it probably won't quite show us because it's just evaluating for smaller and smaller numbers, but it's getting incredibly steep there and approaching some kind of an infinite slope, a nearly vertical slope. That's what appears to be happening there. All right, so there's a pretty interesting couple of functions, I think, that have some nice characteristics to them and not a typical function we see, but we can still take derivatives of. All right, so let's do one more example with this logarithmic differentiation. And this is something, a derivative we would know how to take without this, but it can certainly be helpful. This is not the case where we're going to have something in the exponent to get rid of, but it's just where we have something very complicated. So suppose I have some function like this. And let's throw in a 1/2 x plus 1. All right, we could do this. We could do this with the quotient rule and the product rule and the chain rule, right? You would start with the quotient rule, and then the derivative of the numerator takes the product rule and the chain rule, and the same thing with the denominator. It's doable though, it would get ugly. Here's another option. This isn't necessarily easier, it just gives us an option, and in some cases we might decide to do this. We're going to take the natural log of both sides again. And we have to use another property of logarithms. So we saw last time that logarithms can change an exponent into multiplication. They can also change multiplication and division into addition and subtraction, right? Can make things a bit simpler. So the rules we're going to use are, actually this is true for any base, log base b of xy is the log base b of x plus the log base b of y, and the log base b of x over y is the log base b of x minus the log base b of y. So multiplication becomes addition, division becomes subtraction. This is related. Remember, logarithms and exponents are deeply related, and this is related to the idea that when you multiply two number, the same a variable or number by itself, except it has exponents on each, you add the exponents. Multiplication becomes addition. When you divide, right, x squared over x to the third, you subtract the exponents. Division becomes subtraction. So these logarithms are related to that. If you think about the definition of logarithm and those properties of exponents, you can come up with these rules, okay? So how do we use that here? Well, I wrote it for log base b, but I'm saying it can work for any base, so it certainly works for the natural log. I'm going to think of this as a quotient first, and just think about all this above all this. And so my rule says that I can write this as a subtraction problem. X plus 3 to the 5th, x minus 7 squared. So the two things being divided, the numerator and the denominator, become separate logarithms connected by subtraction. But now each of these is the product of two things. So I can turn each of these into an addition problem. Using that first rule, x minus 7 squared minus natural log x minus 1 to the 1/2 minus natural log of x plus 1. Now I can use that property we used before, taking exponents to the front. 5 natural log of x plus 3 plus 2 natural log of x minus 7 minus 1/2 natural log of x minus 1 minus natural log of x plus 1. Okay, so everything now is expanded into a single logarithm. And now I'm just going to take derivatives of both sides. I'm going to move this over instead of rewriting it. The derivative is always applied from the left. So taking derivatives of both sides. We've seen this one already. We get 1 over y times y prime, or y prime over y. Each of these derivatives is pretty straightforward. They're each a chain rule. So I've got a constant out front. The constant stays there. The derivative of natural log is 1 over x plus 3. The derivative of the inside, though, is just 1. The derivative of x plus 3 is just 1, so I don't need to worry about it. Then we get 2 times 1 over x minus 7. Again, the chain rule, but the derivative of x minus 7 is just 1, so I don't need to worry about it. I get 1/2 1 over x minus 1, same thing, and then minus 1 over x plus 1. And finally, I'll now take y to the other side. So I've got 5 over x plus 3 plus 2 over x minus 7 minus 1 over 2x minus 1 minus 1 over x plus 1. And then the last step is just to write what y is. Y, of course, was that thing we started with. And so I've got x plus 3 to the 5th, x minus 7 squared, x minus 1 to the 1/2, x plus 1, times this whole mess. X plus 3 plus 2, x minus 7 minus 2, minus 1 over x minus 2, or 2x minus 1 minus 1 over x plus 1, right? And there it is. Now, was that simpler than taking the derivative where we have to do a quotient rule, product rule, and a chain rule? Maybe. And certainly as you get used to it, right, these first couple of lines aren't typically lines I would write out. I would if with enough practice, you can jump right to this line. It becomes a bit simpler. And so this might be a nice method for saving some time. If you did it the other way, you'll get, if you do it correctly, and I did this correctly, we should get equivalent functions. They will likely look very different. Do we take a bunch of algebra, common denominators, things like that to put this all together? But we should end up with something equivalent, even though it looks very different. All right, that is it. So that we now have extended ourselves so that we can take derivatives of logarithms and exponentials of any base. And probably more common than taking derivatives of logarithms and exponentials that are not the natural base is using logarithmic differentiation. It's a really handy tool, especially for things like this. I think this is where it's most crucial to use when you've got a function up in a function in the exponent that you need, that's part of the, when you've got, let's write it this way. Let's just, sorry, I'm stumbling over my words. Let's just work symbolically. We can use logarithmic differentiation when we have a situation like this. All right, we take the natural log of both sides and take the exponent down. And then we can take derivatives of both sides. Okay. On the left-hand side, we always end up with y prime over y. Here, it will depend on the nature of these functions, how we treat them, whether we're doing quotient rules or product rules and all sorts of things like that. So I'll just leave that aside. Symbolically, we get something we can take the derivative of on the right, and then we just multiply the original y to the other side, which is of course f of x to the g of x, and then times whatever derivative came out here. Okay, so this is our general. This is the typical place that we will use logarithmic differentiation. Okay, that's it for this one. Thanks everybody. I will see you next time.